Welcome back to the deep dive. Today, we are strapping in for, well, what I think is the single biggest challenge in the future of urban flight. It's this question of how you take an eVTOL, an electric vertical takeoff and landing vehicle, and make it genuinely useful, not just a toy, but something for reliable, long-distance travel.
It's more than just a tech question, isn't it? It's a strategic pivot. It's really about admitting the raw physics of the situation. For years, the whole dream was urban air mobility, UAM, these clean, quiet little hops across the city.
And that's a great promise. I love that promise.
It's a fantastic promise, but we've slammed right into the physical ceiling of lithium battery technology as it exists today.
Right. And we're talking about the best of the best commercial batteries, and they're barely, what, 200, 250 watt hours per
If
kilogram?
you're lucky. And that energy density is like an iron wall. It means your pure electric flight is just fundamentally boxed in. You're limited to these very short routes, maybe 20, 40 kilometers.
Which is fine for a kind of luxury air taxi, but it doesn't scale. You can't build a regional transport network on that.
Exactly. The industry just can't get to real commercial viability with those kinds of constraints. If we want to move serious freight or, a meaningful number of people over real distances, we have to be thinking about regional air mobility, RAM.
Okay, so we're talking routes over 50 kilometers, maybe even 100, 150 kilometers.
That's the target. And to get there, the entire design philosophy has to shift. It's a profound change.
And that shift is really what's at the heart of the engineering blueprint we're diving into today. It's called the P13 series parallel hybrid architecture. It sounds complex, but it seems to be the compromise that unlocks that long-range performance while, and this is key, keeping the safety you need for vertical lift.
Precisely. And the material you shared, it's not just some high-level proposal. This is a top-tier engineering spec. It's been developed with real aerospace rigor. We lean heavily on these structured principles, McKinsey-style top-down thinking, making sure every single requirement traces back to the mission, and making sure it's all MECE, mutually exclusive, collectively exhaustive.
So we're looking at the real blueprint.
We are. This is the foundation derived from the highest safety levels for how this thing actually flies.
So for our deep dive today, we're going to get hyper-targeted. We're zeroing in on the two core components that make this whole complex hybrid system work. We're calling them the digital brain and the mechanical heart.
A good way to put it. The digital brain, that's your motor controller, the MCU. It's not just an inverter. It's the intelligence center running all the algorithms, managing energy second by second. And the mechanical heart is the decoupling clutch, what we call K0. It's the physical switch, the arbitrator of power, and crucially, it's the part designed to fail in a way that guarantees safety.
Okay, so our mission here is to unpack the most critical engineering requirements from these specs. The stuff that ensures both peak performance and, uncompromising airworthiness. Let's start at that strategic level. What's the real driving force behind the P13 design? So when we look at the design philosophy for this P13, the source material just hits you with these two kind of conflicting non-negotiables. You have to maximize range and efficiency, but at the same time, you need absolute, uncompromising safety. Let's start with efficiency, because this architecture, it promises something, well, revolutionary compared to a standard series hybrid.
It really does. The critical driver here is getting rid of conversion losses, specifically during cruise, which is the longest part of any flight.
Okay.
Think about a normal series hybrid. The internal combustion engine, the ICE, runs a generator. Right there, you've got a generator loss, maybe 5–7%. Then that electricity flows to the motor. You get another motor and inverter loss, maybe 8–10%. By the time that fuel energy actually gets to the propeller, you're maybe at 85% efficiency, best case.
And 85% sounds pretty good, but I'm guessing on a long flight, that missing 15% really starts to add up.
It's a killer. On a long-haul RAM mission, that 15% loss is the difference between a profitable route and one where you run out of fuel. So the strategic genius of the P13 is that it allows for mechanical direct drive, and it does that using the K0 clutch.
Thus creating a physical link.
Exactly. It intentionally bypasses the entire electrical path. When that K0 clutch closes, the engine's torque is physically mechanically connected straight to the propeller. We're basically cutting out all the conversion steps. The efficiency just skyrockets to 95, maybe even 98% in the sweet spot.
Wow. So that 10 to 15% gain, that's the whole ball game for making RAM work.
It's the entire reason this architecture exists. It translates directly into more range, more payload. It's what makes it economically viable.
So the K0 clutch, the mechanical heart, it's not just a simple switch. It's the gateway to making the whole platform work financially. Okay, that covers efficiency. What about safety? The standard mentioned is the ESA SC VTOL enhanced category.
Yeah, and that is the absolute bedrock of this entire specification. It sets a bar that is just incredibly high. The probability of a catastrophic failure has to be less than 10 to the minus 9 per flight hour.
And a catastrophic failure means losing the aircraft. Multiple fatalities.
Correct. One failure in a billion hours of flight. Just to give you some context, a system designed to a high-end automotive standard might be orders of magnitude less strict. When you architect a system to that 10 to the minus 9 level, every single decision starts with safety. It forces you into this core concept for the P-13. Single-point failure must not lead to catastrophic consequences.
So if one thing breaks,
The aircraft cannot fall out of the sky. If the engine fails, the electric system must save it. If a key part of the electric system fails, you have to be able to sever that connection instantly. Every component we're about to discuss is just a mechanism to uphold that 1 in a billion target.
that really puts the complexity in perspective. You need it because you're building in all this redundancy and isolation. All right, let's unpack the physical parts that make this all happen.
Okay, so the P-13 system really boils down to 3 key physical components that are managing this power flow.
Okay.
First up, you've got the P1 integrated starter generator, the ISG. This is mounted right on the output shaft of the combustion engine. And its name tells you what it does. It has this dual role. First, in inverter mode, it acts as a really smooth, high-torque starter motor to spin up the ICE. Then, once the engine is running, it flips to rectifier mode and becomes a super efficient generator. It makes electricity to either charge the batteries or send power directly to the main propulsion motor.
And sitting right beside it is the K0, the mechanical linchpin.
That's the K0 decoupling clutch. We call it the physical switch. It's literally between the P1 generator and the P3 propulsion motor shaft. Its state, just open or closed, is the master command that defines what the whole system is doing. It creates or breaks that mechanical link.
And then finally you have the muscle, the P3 propulsion motor.
The P3 is the star of the show, really. It drives the propeller directly. This motor has to be able to provide all that peak power you need for vertical lift, pulling hard from the battery. But it's also more subtle. It provides that torque boost in parallel mode, adding its power to the engines. Its control has to be incredibly precise.
So the whole flight profile from takeoff to landing is basically a dance choreographed by the state of that K0 clutch. Let's walk through those modes.
Right, we can really group them into 3 main clusters, all defined by what the K0 is doing.
Okay.
First cluster is all about quiet, isolated power. We call it pure EV series mode, and this is with the K0 open. With K0 open, the engine is physically disconnected from the propeller. So in pure EV mode, the battery just powers the P3 motor directly. This for your takeoff, your landing, anytime you're near a vertiport and need to be zero emission and quiet.
Or you can run the engine as a generator in that mode too, right?
Exactly, that's series mode. The ICE runs, spins the P1 generator, and makes electricity to power the P3 motor or charge the battery. But the key is the ICE is still mechanically isolated. Any failure in the engine can't physically lock up the prop.
Makes total sense for low-level flight. Then you have the second mode, which sounds like it's all about brute force.
That's parallel boost mode with the K0 closed. The clutch engages, it locks the engine shaft to the drivetrain. We command the ICE to give us max torque, and at the same time we pull peak power from the battery to drive the P3. You're adding the mechanical torque and the electrical torque together. This is for short bursts, a rapid climb, fighting wind shear, and emergency go-around.
And the third mode, this is the moneymaker, the one that hits that 98% efficiency target.
Right. Mechanical direct drive mode, also with the K0 closed. This is your long-distance cruise setting. The ICE is driving the propeller directly through that locked clutch. You're getting maximum fuel economy. In this mode, the P3 motor might just be doing tiny little corrections to hold RPM, or it might be completely off. The whole point is to maximize range by bypassing all those electrical conversion losses.
That's a fantastic overview of the strategy. So let's shift to the digital brain, the MCU. The specs really hammer this point home. It's not just a simple inverter. It's this intelligent hub running all the complex algorithms that hold this thing together.
Yeah, if the K0 is the physical gatekeeper, the MCU is the energy traffic controller. And it has to be an extremely sophisticated one. In aerospace, you just can't have any slop in the controls. It's managing synchronization, power delivery, fault isolation, all of it. And to hit the power density and efficiency targets, well, it had to be built on a pretty revolutionary electrical platform.
Which brings us to this first big requirement, the mandatory move to an 800-volt silicon carbide platform. As an architect, why 800 volts? Why not stick with the 400-volt systems we see in a lot of automotive EVs?
It's purely a decision driven by weight and efficiency.
Yeah.
Two things that are, everything in aviation. Power is voltage times current. Simple physics.
Yeah.
So if you keep the power the same, but you double the voltage from 400 to 800 volts, you cut the current in half. Now, the critical part is that your resistive losses, what we call I squared R losses, they scale with the square of the current. So you have the current, you cut those heat losses by 75%.
75%. So less waste heat, which has to be a huge win in a tight airframe.
It's a massive win. But the even bigger benefit is weight. Less current means you can use thinner, lighter copper cables for the whole high-voltage system. And when you're counting every single gram, that adds up to a huge weight saving. The spec calls for a nominal 800 volts, but the MCU has to be proven to work flawlessly from 600 all the way up to 900 volts. That covers your battery voltage sag under heavy load and the spikes you get during regeneration.
And to handle that 800 volts efficiently, you need the right hardware. Silicon Carbide or SiC MOSFETs.
Mandatory. You have to use 1200-volt rated SiC MOSFETs. And that 1200-volt rating, that gives you the safety headroom you need on an 800-volt system to handle any transient spikes. SiC as a material just lets you switch electricity on and off much, much faster than old-school silicon. We're specifying a switching frequency of at least 40 kilohertz.
And why is that high switching frequency so important?
It's the key to everything, to density to efficiency. Because SiC switches so fast with so little energy loss, you can achieve phenomenal peak efficiency. The requirement is over 98.5%. And when you're that efficient, you generate less heat, which means you can shrink the cooling system, shrink all the other components, and that's how we hit that crazy power density target of over 20 kilowatts per kilogram.
20 kilowatts per kilogram is just a staggering number. But even at 98.5% efficiency, that last 1.5% of 110 kilowatts is still a lot of heat. How do you get rid of it?
Thermal management is just as critical as the electrical design. It absolutely requires a very effective liquid cooling system. We specify either PAO oil or a 50-50 mix of ethylene glycol and water. But the single most critical number is the coolant inlet temperature. It cannot, under any circumstances, go above 65 degrees Celsius. If it does, the sexy modules just fall off a performance cliff and you're looking at an immediate power degrade.
And just to ground us in the numbers, we're talking about 110 kilowatts of continuous power for cruise. But there's this huge 5-second peak current demand of 280 amps.
That 5-second surge, that's your get-out-of-jail-free card in the vertical flight phase. It's the power you need to arrest a sudden descent, fight a gust of wind, or just get off the ground quickly. The entire system has to be proven to deliver that surge on demand, without fail.
Okay, let's get into the smarts of the digital brain, the software. We're starting with the baseline control algorithm.
Right, the foundation for all of this is something called field-oriented control, or FOC. Without FOC, you just can't get the precision you need for flight. FOC is basically a mathematical trick. It lets the MCU control an AC motor as if it were a simple DC motor. It decouples the control of the motor's torque from its magnetic flux.
And decoupling them means you can control them independently.
Exactly. It lets you command a very precise amount of torque instantly at any speed from a dead stop all the way up to 12,000 RPM.
When the pilot makes an input, FOC is what ensures the motor responds immediately and smoothly. It's non-negotiable for fly-by-wire.
And that as the vehicle speeds up, for high-speed cruise, you need something called weak magnetic control. What's that doing?
Okay, think of it like this. Every electric motor has a natural top speed, its base speed. It's limited by the voltage of the battery. At that speed, the motor's own spinning magnets create a back voltage, a back EMF, that perfectly opposes the battery voltage. You can't go any faster. Field weakening is the trick to get around that.
How does the trick work? The MCU intentionally injects a little bit of current that works against the motor's own permanent magnets. It's literally weakening the magnetic field.
Yeah.
When you weaken the field, you reduce that back EMF, which then allows the battery voltage to spin the motor even faster. It's like adding an overdrive gear. It's essential for hitting efficient high cruise speeds.
Then we have regenerative braking. That's obviously about efficiency, but it sounds like it's a control tool too.
It's absolutely both. As the aircraft descends, the air rushing past the props turns them into little windmills, and that turns the P3 motor into a generator. The MCU has to take that power and efficiently stuff it back into the battery. So yes, you're recovering energy and extending your range, but from a control standpoint, it gives the pilot this really smooth, predictable electromagnetic braking force. It's much smoother than just using aerodynamic drag.
Okay, those are the performance controls. But there's one function here that seems totally unique, and it's all about mechanical protection. active damping. This is where the digital brain literally protects the mechanical heart.
Active damping is a mandatory function, and it exists solely because this is a hybrid. A combustion engine is, well, it's a series of controlled explosions. Every time a piston fires, it sends a little torque pulse, a vibration, down the crankshaft. If you just connected that rattling, vibrating shaft directly to the clutch and the propeller, you'd shake the whole thing to pieces. It would cause massive wear and fatigue.
So you're using electricity to smooth out mechanical pulses?
That's a perfect way to put it. The MCU for the P1 generator is constantly listening to the engine speed with microsecond precision. The instant it senses a torque pulse from a piston firing, it injects an exactly opposite electrical torque pulse into the generator. It's an anti-phase Quaxis torque current. It's like active noise cancellation, but for vibrations. The electrical pulse cancels out the mechanical pulse, and the result is a perfectly smooth shaft going into the clutch.
Incredible. Okay, let's talk about the built-in safety layers, starting with the high voltage interlock, or HVIL.
The HVIL is your first line of defense for anyone working on the aircraft. It's a simple, low-voltage circuit that runs in a loop through every single high-voltage connector. If that loop is broken, if a technician starts to unplug something, the MCU's hardware logic has to kill the power output.
How fast does that have to happen?
In less than 10 microseconds. That's not a software decision. It's baked right into the hardware logic. It has to be that fast to prevent any chance of electric shock.
But even with the output off, you've still got 800 volts stored in the system's capacitors.
Right, which is why you also need active discharge circuitry. The instant that HVIL loop opens, the separate circuit kicks in and starts to bleed that stored energy away safely. The mandate is that the voltage on the main bus has to drop below 60 volts, the safe-to-touch level within 5 seconds. It's a critical safety step for ground crews.
Next up is a concept I love, thermal derating. You call it elegant degradation. So instead of just shutting down, it gracefully backs off.
In aviation, predictability is always safer than an abrupt failure. If the MCU sees its internal temperatures getting too high, the last thing you want is for it to just cut all thrust. That would be catastrophic. So instead it goes into thermal derating. It smoothly and automatically starts to limit the maximum power output. The pilot still has control, the aircraft is still flying, but the performance is reduced. It prioritizes keeping the aircraft controllable over protecting the component.
And the final layer of redundancy, what happens if the main position sensor for the motor fails in flight?
That's where the sensorless control backup comes in. Normally, the MCU relies on a super precise sensor, a resolver, to know the rotor's exact position for FOC to work. If that resolver fails, the MCU has to be smart enough to instantly switch to a backup algorithm. It uses a sliding mode observer or something similar. It basically figures out the rotor's position just by looking at the voltage and current. Performance is a bit degraded, but it keeps the motor spinning and producing thrust, which lets the pilot fly to a safe landing.
Let's shift now. We've covered the digital brain. Now to the mechanical heart, the K0 decoupling clutch. We know its role in efficiency, but the spec makes it clear its primary job is failure isolation.
That's right. This one component, its entire design philosophy, has to be focused on safety and physically isolating one part of the powertrain from the other. It's carrying the full weight of that 10 to the -9 mandate.
So let's start with the basic choice of clutch. The spec calls for an electromagnetically actuated dry friction clutch. Why that specific type?
It's a very deliberate choice over, say, a wet clutch that you might find in a car's transmission, which is bathed in oil.
And why is a dry better here?
Two big reasons. First is drag. A wet clutch, even when it's open, always has some parasitic drag because of the viscous oil between the plates. It's small, but it's always there, and it would constantly be robbing you of precious range when you're in pure EV mode. We specify that drag torque has to be less than 1 Newton meter. Trivial. Second is cold weather. Oil gets thick when it's cold, which makes wet clutches slow and sluggish. A dry clutch doesn't have that problem.
And getting rid of hydraulics for the actuation seems like a no-brainer for safety.
Absolutely mandatory. We have to use electromechanical actuators, or EMAs. Hydraulics mean flammable fluid, high-pressure lines that can leak, and again, that cold weather viscosity problem. EMAs are cleaner, faster, more reliable, and much easier to diagnose if something goes wrong.
Okay, now we get to what seems like the single most important design feature in the whole document. This idea of fail-safe open, or power to lock.
This is the absolute foundation of the P13 safety case. It completely flips the normal logic on its head. It means that you have to be actively applying electrical power just to keep the clutch closed, or engaged. If that control power fails for any reason, a wire gets cut, a controller freezes, anything, a set of powerful pre-stressed springs inside the clutch mechanically and automatically force it into the open decoupled position.
So, to be totally clear, if the control system for the clutch dies, the engine is guaranteed to be physically disconnected from the propeller.
Guaranteed. It prevents the ultimate nightmare scenario: a seized engine physically locking up the propeller. If the engine seizes and the prop stops turning, the aircraft becomes a brick. By mandating fail-safe open, any power failure immediately isolates the bad actor. It ensures the P3 electric motor can always use its own battery power to keep the prop spinning and bring the aircraft down for a controlled landing.
That's the worst case scenario. But for just normal day-to-day flying, the clutch has to be incredibly smooth and fast. Let's talk about synchronization.
Yeah, you can't just slam it shut. That would be catastrophic for the machinery and terrifying for the passengers. Before the command is given to engage the clutch, the VCU has to use the P1 motor to perfectly match the engine speed to the propeller's speed. The rotational speed difference, the delta RPM, has to be less than 50 RPM.
50 RPM. When things are spinning at thousands of RPM, that sounds incredibly precise. What if it's off?
The system will block the command. It won't let it engage. If you try to engage with a bigger speed mismatch, you'd get this massive mechanical shock wave through the whole drivetrain. The jerk would be violent. So that synchronization is a hard requirement.
And what about the speed of the engagement itself?
It has to be fast. The engagement locking time is specified at 200 milliseconds or less. That ensures there's no perceptible lag in thrust when you switch modes, but the emergency separation time has to be even faster. If a major fault is detected in the engine, the clutch has to be fully open in 100 milliseconds or less. You need to isolate that fault immediately.
And you mentioned jerk. The spec puts a hard number on it. Mechanical jerk has to be below 0.2 gram megams. How do you even achieve that?
The jerk is the rate of change of acceleration. Is what makes things feel snappy or violent. And keeping it below 0.2 gram means the torque handover has to be completely imperceptible. To do that, you need this perfect ballet between the MCU smoothly ramping the torque and the EMA smoothly applying the clamping force on the clutch. It's what makes it feel like an aerospace-grade system, not an industrial one.
And finally, durability. This thing is going to be cycling constantly.
Constantly. So the design lifetime is specified to exceed 100,000 engagement cycles. That's what's needed to meet the demands of commercial service, keeping maintenance costs down and the aircraft in the air.
So it's clear these are incredibly advanced components. But in aviation, they're useless if they're not integrated with absolute rigor. Let's talk about how the digital brain and mechanical heart are forced to communicate perfectly.
Right. This is where the rubber meets the road. The best component in the world is a liability if it isn't airworthy, and that all starts with bulletproof communication and design assurance.
The system is sending critical torque commands 1,000 times a second. What kind of communication bus can handle that?
You can't have a single dropped message.
Yeah.
Not one. So all critical commands have to run over dual redundant buses. Specifically, aviation standards like CAN-FD, which is ARIN-C 825 compliant, or even better, ARIN-C 664, which is deterministic Ethernet. And that 1 kilohertz update rate means a new command is arriving every single millisecond. That's the speed you need for the MCU to react instantly and maintain flight stability.
And when the main computer asks the clutch, are you open or are you closed? The answer can't be a guess.
No, it has to be unimpeachable. You can't just infer the clutch's position based on how much current the actuator is drawing. That's not good enough. The CADAR assembly must have its own independent position sensors, dual Hall effect sensors, redundant microswitches, something physical that provide a hard, confirmed locked or open signal back to the control unit. It's the only way to be sure.
Let's talk about the physical connectors, especially at high altitude. You mentioned something called corona discharge.
Yeah, that's a classic aerospace problem.
Oh.
Air is an insulator.
Right.
But as you go higher, the air gets thinner, the pressure drops, and low-pressure air is a much worse insulator. So at 40 or 50,000 feet, the 800 volts can actually start to ionize the air around the connectors, creating this little electrical discharge, a corona. Over time, that degrades the insulation and can lead to a catastrophic arc flash.
So how do you prevent that?
You have to use specialized aerospace connectors, things like the Amphenol HV338 and 999 series. They're designed with longer physical paths for the electricity to travel and special materials to prevent that discharge from ever starting, even in the thin air at high altitude.
Now, for the big picture, the regulatory side, what separates a cool prototype from a certified aircraft component is this whole process, the V model.
The V model, which is governed by SAE ARP 4754A, is all about traceability. It's a structured process that ensures every single line of code, every hardware choice, every test you run can be traced all the way back up to a high-level safety requirement. If you can't show that unbroken chain of logic from the 10 to the -9 requirement all the way down to a specific test result, you're not airworthy, period.
And the ultimate measure of that is the design assurance level, or DAL. Why is DALA mandated for the MCU software and hardware?
DAA is the highest level there is. It's reserved for systems where a failure would be, by definition, catastrophic, total loss of the aircraft. Since the MCU and the K0 have direct control over propulsion, any failure is directly linked to flight safety. So the core control logic has to be DLA. It means exhaustive testing, multiple independent reviews. It's the most expensive and time-consuming way to develop anything, but it's the cost of entry for commercial aviation.
And the legal framework for all of this is EA SCE 19.
That's the one. That document lays out the specific rules for how you prove a hybrid electric system is safe, how you prove your insulation is good enough, how you prove your fault tolerance. It's the rulebook you have to follow to get certified.
Okay, let's get into the really dramatic stuff. The failure analysis. How the system is designed to handle the absolute worst-case scenarios. First up, uncommanded loss of thrust control.
Right, so to mitigate that, we use what's called a dual-winding, dual MCU architecture for the P3 propulsion motor. So instead of one big motor, you can think of it as two smaller, completely independent motors wrapped around the same shaft. Each has its own set of windings, and each winding is powered by its own, totally separate MCU.
So if one MCU just completely shorts out or its software crashes.
That MCU and its half of the motor windings are instantly and physically disconnected from the system. The other, healthy MCU and its windings just keep on working. You're guaranteed to still have at least 50% of your rated torque. The aircraft remains fully controllable. It's not just a backup. It's designing the system to degrade gracefully.
And now for the big one, the double failure. The K0 clutch gets jammed closed, and then the engine seizes.
This is the acid test for the whole safety concept. We have to prove through analysis that this combined failure has a probability of less than 1 in a billion. So we're assuming the fail-safe spring has failed, the clutch is stuck, and then the engine locks up solid, basically welding the dead engine to the propeller.
So what's the solution to that?
Brute force. The P3 electric motor has to be designed with enough overload torque capacity to physically power through it. It has to be powerful enough to spin the propeller and drag the entire seized mechanical mass of the dead engine along with it. It's an incredible requirement. It means a huge chunk of the P3 motor's power is reserved purely to overcome a catastrophic failure in the other half of the system.
That's amazing. Okay, so all this brilliant design means nothing if you can't prove it works. Let's talk about testing and verification.
Exactly. The right side of that V model, it's where theory gets brutally tested by reality. You have to prove you've met that 1 in a billion target.
So where do you start? The first stage is called copper bird testing.
Right. The copper bird is a lab test. It's all about the electrical system. You take the real 800-volt battery, the real MCUs, the real high-voltage wiring, and you hook it all up to dynamic loads on a bench. You're looking for electrical integrity. Does the high-frequency switching create electromagnetic interference, EMI, that could mess with other avionics? Is the power quality clean?
And this is where you test the safety responses.
This is where you do fault injection. You systematically and deliberately break everything. You short out sensor signals. You inject bad data onto the CAN bus. You physically open the HVIL loop. And you verify with an oscilloscope that the safety responses happen within the specified time. Does the PWM shut down in under 10 microseconds? Does it switch to sensorless control seamlessly? If it fails any of those tests, it's back to the drawing board.
Once the electrical side is proven, you move to the Iron Bird.
The Iron Bird is the big one. It's a full-scale, one-to-one replica of the entire propulsion system, all mounted on a massive steel test rig on the ground. You've got the real engine, the real motors, the real clutch, a device that simulates the load of the propeller, and the real battery system. It's the whole powertrain.
And the main goal here is to test the mode switching.
Thousands and thousands of times. You run it through every conceivable flight profile, EV takeoff, boost, cruise, back to EV for landing. Over and over. You have sensors all over it measuring everything, and you are verifying, cycle after cycle, that the mechanical jerk never exceeds 0.2 grams. This is also where you prove the clutch can survive its 100,000 cycle lifetime under real mechanical stress.
And after all that, you still have to prove it can survive the environment of flight itself.
That's environmental testing to the DO 160G standard. The components go into specialized chambers to simulate the absolute extremes. You have severe temperature cycling, taking them from deep freeze Arctic conditions of -55 Celsius all the way up to +85 C, which is what it might see in a hot engine bay on the ground.
And the high-altitude
You
test.
put it in a vacuum chamber to simulate 50,000 feet. This is where you prove your special connectors actually work, that you don't get any corona discharge when the air pressure drops to almost nothing.
Yeah.
And finally, you bolt it to a shaker table for hundreds of hours and subject it to extreme engine-mounted vibration. We call it Curve W. It's a brutal test to make sure nothing cracks, nothing chafes, nothing breaks loose.
So after all that, the specs boil it down to a few final non-negotiable numbers for acceptance.
These are the pass-fail criteria. For the MCU, its efficiency has to be 98.5% or better at a typical cruise power setting. For the K0 clutch, engagement time under 200 milliseconds and drag torque under 1 Newton meter.
And the safety systems.
They have to be perfect. The HVL cutoff has to be proven to be faster than 100 milliseconds. And the fail-safe open mechanism for the clutch has to have a 100% success rate through every single test. One failure, and the whole design is rejected. It's not airworthy.
This has been just an incredible look behind the curtain. It's so clear that this P13 hybrid system isn't just some simple compromise. It's this incredibly sophisticated solution that's born from the hard limits of physics and the absolute demands of aerospace safety. I feel like we've seen two sort of defining paths emerge from this.
I think that's right. The first is the power platform itself. That decisive move to 800-volt silicon carbide technology. It's really the only way to get the power density and that 98.5% efficiency you need to make long-range flight viable.
And the second is that life-saving mechanical defense, the whole fail-safe open K0 clutch design. It's the physical bedrock of the entire safety case, making sure you can always have propulsion, even if the engine literally explodes.
Yeah, the success of the whole thing really hinges on that perfect synergy between the digital control of the MCU and the physical isolation of the K0 clutch. And it's all proven through that brutal DLOA process and the physical reality of the Iron Bird. It's a perfect blend of modern electrical engineering and, old school aerospace safety principles.
It is, and it's amazing how everything traces back to that 1 in a billion number. We spent a lot of time on that idea of the P3 motor needing enough overload torque to physically drag a seized engine.
That really is the most profound takeaway, technically.
And it feels like it fundamentally changes the whole idea of redundancy. It's not just if system A fails, system B takes over. It's more like the functional component must be powerful enough to physically overcome the catastrophic failure of the non-functional component.
That is the new definition of airworthiness for these complex blended systems. Isolation is one thing, but the ability to survive by overpowering a mechanical failure with electrical control. That's the ultimate safety net.
So, a final thought for you, our listener, to chew on. We've seen a digital brain, the MCU, used to cancel out mechanical vibrations. We've seen an electric motor, the P3, used to overpower a seized engine. As engineers keep blending these systems, what other old-school aerospace safety ideas might have to be totally redefined? Where else might we see intelligent digital control being used to physically overpower a fundamental mechanical failure? Something to think about.
Indeed, it's that kind of thinking that's going to define this new era of aviation.
Thank you for joining us on the Deep Dive. We hope you feel a little more informed about the incredible engineering that's making the future of flight a reality.